Have you ever stopped to think about how you do, well, anything? How a thought, just a little flicker in your mind, makes your hand move in less than a second? Well, today, we're going to dive into the amazing electrical language of your nervous system, the nerve impulse.
Right, so that's the big question, isn't it? How does a thought actually turn into an action? It's not magic, I promise. It's this beautifully coordinated electrical event, a tiny spark that travels faster than you can even imagine. And we are going to break down exactly how it all works, step by incredible step.
Okay, first things first. Before a neuron can send any kind of message, it has to be ready. You can think of it like a tiny biological battery, just sitting there, fully charged, waiting for the signal to let go of all that energy. This is its resting stage.
Now, this state of readiness, it has a name. It's called the polarized state, and you can see why. There's a clear separation of charges. You've got all this positive charge on the outside of the neuron's membrane and a negative charge on the inside. This difference, this electrical tension, that is the stored energy, and it is absolutely crucial for everything that's about to happen.
And we're not just talking about some vague difference here. It's a very precise, measurable electrical charge. The inside of that neuron is sitting at negative 70 millivolts compared to the outside. That specific number is the resting membrane potential. And holding on to that number, well, that's the neuron's number one job when it's waiting.
So how in the world does a neuron even create this negative 70 millivolt charge? It's a really delicate balancing act. First, the cell's membrane is a bit leaky to potassium ions. That's the K+ you see here. So they tend to sneak out, taking their positive charge with them. Second, you've got these big negatively charged proteins that are just stuck inside the cell, making the inside even more negative. And finally, there's a special little pump that is working around the clock to keep everything just right.
But of course, the neuron doesn't just sit around at rest forever. When it's time to send a signal, all that stored up energy gets released in this dramatic, lightning-fast event. And this is the main event, the action potential. It's a total all-or-nothing electrical firestorm.
Nothing happens without a trigger, right? A little message from another neuron or some kind of sensory signal acts as a stimulus. But here's the thing. It can't just be any tiny little nudge. It has to be strong enough to push the neuron past a critical tipping point. We call that the threshold. And once you cross it, well, there's no going back. The chain reaction is unstoppable.
And this is exactly what happens next. The very moment that threshold is crossed, these special little doors, the voltage-gated sodium channels, they fly open. This creates a pathway for a massive flood of positively charged sodium ions to rush into the neuron, completely overwhelming that negative charge that was there just a moment before. And what you get is this incredible reversal. I mean, look at this. We go from positive out and negative in during the resting state to suddenly being negative out and positive in. The polarity is just completely flipped on its head. This dramatic switch is the core of the nerve impulse. It is the spark. This process is called depolarization. And get this, so many positive sodium ions rush in that the inside of the cell doesn't just get to zero. Oh no, it skyrockets all the way up to positive 30 millivolts. This is the absolute peak of the action potential, the very height of this electrical spike. And here's the truly mind-blowing part. This whole thing, from resting at minus 70 all the way up to this peak of plus 30, it all happens in about half a millisecond. That is just an astonishing speed. It's the reason your reflexes feel instantaneous. It's why you can pull your hand away from a hot stove before your brain is even consciously registered to pain.
Okay, so the neuron has fired. Awesome. But now what? It can't just stay in this fired-up state forever. If it wants to send another signal, it has to reset itself, and it has to do it super fast. This brings us to the reset sequence, a process we call repolarization.
So how does it hit the reset button? Well, right at the peak of that action potential, those sodium gates snap shut, stopping the inflow of positive ions. Immediately after that, a different set of doors, the potassium gates, swing open. This lets positive potassium ions rush out of the cell, which starts bringing that internal charge back down toward negative territory. Now, the potassium gates, they're kind of slow pokes. They take a little bit too long to close. Because of this, the neuron can briefly overshoot its resting target, dipping down even further to around negative 90 millivolts. And that little temporary dip, we call that hyperpolarization. So how do we get from that overshoot precisely back to our perfect negative 70 millivolts? Well, enter the hero of our story, the sodium-potassium pump.
This little molecular machine is a workhorse. It's tirelessly using energy to pump 3 sodium ions out for every 2 potassium ions it brings in, perfectly restoring that delicate resting balance. This process is so vital that it could actually use up to a third of your body's entire energy budget when you're just sitting still.
Now, if you thought that was fast, hold on. Some of our neurons have a kind of biological superpower that makes them even faster. With these neurons, the impulse doesn't just flow down the line. It actually performs this incredible acrobatic feat.
This superpower has a name: saltatory conduction. In certain neurons that are insulated with this fatty stuff called myelin, the action potential doesn't happen along the whole membrane. Instead, it only regenerates itself at these very specific gaps in the insulation, which we call nodes.
And what this means is that the electrical signal literally leaps from one gap to the next. This jumping impulse travels many, many times faster than one that has to crawl smoothly along the entire length of the neuron. This is what allows for incredibly rapid communication over really long distances, like the signal from your brain all the way down to your toe.
All right, let's just recap this incredible journey real quick. We start at rest, nice and stable at -70 millivolts. A stimulus hits, triggering depolarization, which rockets the charge up to +30. Then, repolarization kicks in, bringing the charge back down, overshooting just a little bit to -90, before that amazing pump restores the perfect -70 resting state. All of this in just a couple of milliseconds.
This tiny, intricate electrical dance is the fundamental basis of everything you think, everything you feel, and everything you do. It's happening millions of times a second across billions of cells inside your brain right now. So the next time you have a thought, just remember the incredible journey it took. A silent, electric storm that makes you, you. What does that make possible? Well, it makes possible every memory, every emotion, every action. It makes possible